Kirchhoff's laws, or Kirchhoff's rules, actually, is the experiment that we want to talk about today. And Kirchhoff's rules are rules that will allow you to calculate the current through a complicated circuit containing as many resistors and voltage sources as possible, but nothing else. No capacitors, no other circuit elements. So let me draw a picture of the circuit you're going to be building on the PC board, and we'll talk about the PC board and so forth when we get over to look at the actual experiment. So here's the circuit. A circuit is a complete path for current to flow. So here's a circuit. This is a resistor. This symbol here is a resistor. This symbol here stands for current. And if we haven't talked about it, if you haven't seen this last week, we need to talk about Ohm's law very briefly. And this says the voltage drop when current goes through a resistor is given by this very simple linear relationship. So when current goes through a resistor, resistors resist the flow of current. It takes some voltage, it takes some energy in a sense to get the current through a resistor. And so when you get through the resistor, you're at a lower voltage here than you are here. So there's a voltage drop when the current goes through a resistor. And that will become important in Kirchhoff's rules. Okay, so here's a resistor. Here's a current going through a resistor. We can't have a current going through a resistor without a complete circuit. So here is what the circuit's going to look like. This is a symbol for a battery. The small bar is the minus side. The long bar is the plus side. And so here's a circuit with a couple of resistors in it. Now it's a complete circuit. Current can flow through that. I'm going to call this resistor R3 for reasons that you'll see in just a minute. We'll call this voltage V1. So this is current I1 produced by voltage V1 sending through the circuit. Now we don't need Kirchhoff's rules to figure out what's going on here. We have two resistors in series, and if you've done the Wheatstone Bridge Lab, you know how to add resistors in series. You just add them. If this is 10 ohms and that's 20 ohms, then the total resistance is 30 ohms. It's really simple. So if this were just the circuit we were talking about, this would be a very simple circuit. We could replace these two resistors by, if that's 10 and that's 20 ohms, by one 30 ohm resistor, and simply use this equation to figure out how much current would go through a 30 ohm resistor with a certain size voltage, 1.5 volts, 3 volts, whatever it is. And we would find out that the current is equal to the voltage divided by the resistance. So that's really very simple circuit analysis, but we're going to make this more complicated by adding another resistor, we'll call it R2, and another voltage source, V2, to the circuit. Okay, so this is going to be the circuit you're going to set up on the PC, the printed circuit board. Now, this is a lot more complicated. It just looks like it's a little more complicated, but it's a lot more complicated because these two batteries are both trying to push their own currents. Let's say this is current I2 here. And trying to push these currents through the circuit, and maybe trying to push current backwards through this, or they're sort of competing for the grand total current flow through the circuit. And that's the benefit of using Kirchhoff's rules, because we can figure this all out very nicely. So let's take a look. We'll call this A and we'll call this B. Those are junctions where wires come together, and they're called junctions. Okay, so these currents are coming in, I1 and I2 coming in, and I3, I'm just assuming, coming out. So what I've done is make some assumption as to which way those currents flow. And since this is the plus side of these batteries, and this is the minus side of these batteries, and we're talking about Ben Franklin's supposed flow of positive charges to keep life simpler, they go from plus towards minus, and so the currents probably flow this way on this side of the circuit and this way on this side of the circuit. So I'm going to draw an I1 in this direction here and an I2 in this direction here. And let me discuss Kirchhoff's rules. The first rule is called the Junction Rule. And let's look at junction A, for instance. These wires here are what are called hookup wires, and we're assuming that they have no resistance, at least no resistance compared to the resistance here. These are called discrete or lumped circuit elements, which means all the resistance in the circuit is here and here and here and nowhere else. And all the voltage is here and here and nowhere else. So they're lumped circuit elements or discrete circuit elements. And so that's the way we kind of interpret when we look at this picture. So we have this connection here, and at junction A, we have two currents coming in and one current coming out. At least I've assumed that. And that's the way you should do this, is take your best shot at guessing which way the current probably flows. And as you'll see later on, when we get the answers, if you come up with a negative sign, that means it flows the other way. Not a big deal. So you can't lose on this. So take a stab at which way the currents flow. I think they flow this way. And if I'm wrong, I'll get minus signs, which means they flow the other way. So here's Kirchhoff's rules. By the way, the first rule of Kirchhoff is that it has two H's and two F's. Kirchhoff's rule. So the first rule of Kirchhoff is called the junction rule, and it says the sum, that's sigma, big sigma for sum, of the currents at a junction all adds up to 0. Now that presupposes we have plus currents and minus currents. So, and it makes sense to me to say a current going into a junction is plus and a current coming out of a junction is minus. So that's going to be my current convention. So currents going into a junction are plus, currents coming out of a junction are minus. So let's take that general rule here. This could be a way more complicated circuit. We could still analyze it using Kirchhoff's rules as long as there's only resistors and voltage sources in the circuit, nothing else. So the junction rule here says at junction A, so we can say at junction A, the currents going in are I1 and I2, and the currents coming out is I3, so it's minus. So they all add up to 0. Or I can say that I1 plus I2 equals I3. Same thing. So at junction A, this is my Kirchhoff's junction rule. Kirchhoff's other rule is that the voltages across around a loop have to add up to 0. That's a little more complicated in terms of what does that mean, what's plus and what's minus. Okay, so we have to figure that out, or we have to define that and describe that in terms of a convention. So this says that when I follow around in a loop, and which means I'm coming back to where I started, and I like to start at the bottom of a battery here, and I'm going to just call that 0 arbitrarily. When I go around this loop, let me draw a picture, indication of which way I'm going to go around in that loop. So this doesn't mean current or anything. It means I'm going around that loop in a clockwise direction in my mind, starting here. So I'm going to start here and go around that loop and come back. And over here, because Ben Franklin currents come out of plus voltages and go into minus voltages, I'm going to assume that that I'm going to follow around the loop this way, sort of counterclockwise. So I'm going to start here and go through this loop counterclockwise. So these are not currents. These are ways that I follow through that loop and consider where are the voltage changes, the voltage increases and the voltage decreases around the loop. Okay, so if I start here and go through this voltage from the minus side of the battery to the plus side of the battery, it's pretty obvious that I'm going to call that a plus change. That is, the voltage goes from 0 to V1 over on this side of the voltage supply. So a plus voltage goes from minus to plus through a battery, in a battery. So, and we talked, okay, so the voltage here is going to be 0. I'm just call it 0. It's ground, my reference. The voltage here is going to be V1. That's what the battery does. It changes the voltage so that voltages can produce currents through resistors. So we arrive at resistance R1. There's no resistance in these wires. We're going to assume they're hookup wires. And so we're going to apply Ohm's law at this voltage, voltage of this current going through this resistor, which means on the way through the resistor, the voltage goes from V1 down to some lower value. We lose voltage when we follow through a resistor in the direction we think the current flows through the resistor, or we have assumed the current flows through the resistor. So it's going to be a lower voltage here. Then we're going to go through this resistor in the same direction that we've decided to go through with this current. And that means there's a voltage drop across this resistor, and those two drops lead us back to this point here. There's no resistance in this wire. Therefore, the voltage increase here is lost here, and here these two losses add up to that gain. So the left loop voltage equation looks like this. We start from here, and the voltage goes from I'm going to just call it 0 to V1 plus V1. I go through the resistor R1 in the direction I'm assuming the current goes through it. Again, don't get these directions confused with the current directions. I picked the current directions with some thought, but arbitrarily, and that's the way the currents are going. This little red circle indicates this is just the way I'm going around this loop mentally in my mind from one circuit element to the next, and back to where I started. Okay, so when I go through this, there's a voltage drop, and the voltage drop by Ohm's law is given by I1 times R1. So it's minus I1 R1. And I go around the corner here through this resistor, and I'm going through this resistor also the same way that I've assumed the voltage to go through. So it's another drop. So it's minus I3 R3. That brings me back over to here, which means I've gone through a loop. Wait till it's over. Okay, so I've gone through this the first loop, the left loop, and those voltage changes add up to 0. Those voltage increases and decreases add up to 0. I'm going to do the right loop. Okay, and I'm going to start here and go through this in this direction, the red circular direction. And so we have V2 plus V2, I'm going from minus to plus, and I'm going through this resistor R2 in the direction I'm assuming the current to go through it, and likewise over here. So we have minus I2 R2 minus I3 R3 equals 0. So here are my three Kirchhoff's rules equations. If you have a more complicated circuit, you have to have additional rules saying how many current or junction equations you need to write, how many loop equations you need to write. This circuit has 3 branches. Current I1 is the same all the way from here all the way to here. Current I2 is the same from here all the way to here. And current I3 is the same through that middle branch. So you have 3 branches. That is a part of the circuit in which a certain current can flow. And so we have to have 3 equations because our unknowns are these 3 currents. So we presumably know V1, and we know V2, and we know R1 and R2 and R3. We can measure those with a meter, with a voltmeter and an ohm meter, and record those values. So we know everything about these equations except I1 and I2 and I3. So I want to solve for I1, I2, and I3. Now the theory behind Kirchhoff's rules is pretty interesting, because you might be saying, well, wait, now these two batteries are forcing current. They want to force current their own way through the circuit, and so who wins, or how do you figure out the grand total final answer? Well, this relies on what's called the superposition principle, which basically says I'm going to write an equation like this equation for the left loop, and I'm going to ignore what's going on over here. And you really can't do that, but you can at least for a while ignore that. And so that's what this equation means. I'm not even considering what's going on over here, how this voltage is contributing to the current flow through the circuit. I'm just going to go around this loop here and pretend that's the only loop there is. And I'm going to do that for the right loop also. I'm going to forget this loop here and look at the currents here. So don't forget, current I2 goes through here and current I3 goes through here. Each branch has its own current. However many things are in that branch in series, they all have the same current. Okay, so that means that I can mathematically solve these as three independent current equations, or three independent equations involving current, because I know the voltages and I know the resistances in the circuit, but I don't know the currents. So you want to solve these equations, and I'm not going to go through that solution here. There's two ways to solve equations, or three ways to solve equations. You can do it by substitution or elimination, or you can use a matrix if you know how to work with those. So let's not take the time to figure out how to do that. We can do that in the lab once you get this data. This is the lab which you can perform very quickly, and you want to stick around and do the data analysis while you're here, while you have an instructor to kind of help you through the solving of these three simultaneous equations for currents I1 and I2 and I3. So again, the process is to solve these simultaneously, and we're using Kirchhoff's rules to do that. We're using the concept of partial currents, or what we call the superposition of partial currents, to figure this out. It really does work wonderfully well. You can, to set up the left loop equation, you ignore this part of the circuit. To set up the right loop equation, you ignore this part of the circuit. But you have to realize they all work together, which is mathematically why you have to solve these equations simultaneously to get the one and only I1 and the one and only I2 and the one and only I3, the grand total current that goes through each branch in this circuit. Okay, so that's really Kirchhoff's rules. All you need to know is V1 and V2 and R1 and R2 and R3, and you can calculate the currents. We can measure these ahead of time. By the way, when we do the experiment, you want to measure V1 while a circuit is in operation, and you want to measure V2 while a circuit is in operation. And we'll talk about that later in class, because there's what's called an internal voltage drop, and so that depends on the current being produced and flowing out of that battery. So we want to measure the working voltages, what are called the terminal voltages of those voltages. So hook up the circuit, get it working, measure the voltage V1 and V2 while the circuit is working, measure the resistances before you put them in the circuit, and then you can apply Kirchhoff's rules to get the answer. So I'm going to solve these simultaneously. So solve those simultaneously to get the solution. Now, please don't use what I'm about to say to plug in some numbers in these equations here, because this is a check. This is a check of your answers. Okay, so there's another way to analyze this experiment, the circuit, by more or less directly finding out what I1 and I2 and I3 are, not going through all that mathematics, but I want you to go through the mathematics, and I want you to use what I'm about to say as a double check in your results. Okay, so here's what you do for the second part of these for this circuit. You measure V1 and V2. You already measured R1 and R2 and R3. While a circuit is in operation, when you measure V1 and V2, you want to take your voltmeter. There's a voltmeter, and you want to hook it across here and here with clips and measure the current through, measure the voltage across, we'll call that V sub R1. That's the voltage across R1, not to be confused with V1, which is the voltage running the circuit here. V sub R1, so V sub R1 is equal to I1 times R1, which means if I can measure that with a meter, I1 is equal to V sub R1 over R1, which R1 you've already measured, V sub R1 you're getting from the voltmeter. So this will give you very quickly, very directly, the answer to what is I1. But use that as only a double check, please, a check of your answers over here. These are your Kirchhoff's rules applications to find the currents. And similarly, we can measure VR2 by hooking temporarily across this resistor, and we can hook the voltmeter across R3 to measure VR3 and get the value for I3 by VR3 divided by R3. So these are, again, checks for your, or rather more sophisticated mathematical calculations of I1 for I1 and I2 and I3. And part B is simply change these battery values. You've got 4 values, roughly 1.5, 3, 4.5, 6 volts from your battery pack here and here. You can select any voltage you want in both of those. You can even hook them up backwards, put the plus here and a minus here, flip a couple of these resistors around, exchange R1 and R3, and then just do the experiment over again. Go through Kirchhoff's rules analysis, and then also use Ohm's law to figure out the currents in each of these resistors. Again, the error analysis is really pretty simple. Every time you use one of these meters to measure anything, it has an error. And you can figure out the error from the little owner's manual or the operation manual. Let's say that, let's just make up some numbers. Say that the error in this voltmeter is 1% and the error in the resistors is 0.5%. I don't know what they are. You'll have to look it up on the table. So if this is 1% and that's 0.5% and that's 0.5%, you have a 2% total error in this current loop here. And with Ohm's law, if this meter is accurate to 1% and the resistor is accurate to 0.5%, then you have an error of 1.5%, measuring the voltage across the resistor to calculate I1 using using Ohm's law, not Kirchhoff's laws. So the Kirchhoff's laws are going to give you, because actually you have the error in this resistor and this resistor and this resistor, this voltage and this voltage, they all are working together in Kirchhoff's rules. You have to add up the errors in these 2 voltages and these 3 resistance measurements to get the error in your answer using Kirchhoff's rules, whereas for Ohm's law, you only need the error in the voltmeter reading and the error in the resistor, which you've already determined, and those 2 errors, whatever those percents are, add up to give you the error from Ohm's law. So those 2 ranges, the error in your values for the 3 currents using Kirchhoff's rules, which is going to be a little bit bigger than the error that you get from measuring the voltage across the resistors and getting the currents using Ohm's law. The error here's going to be smaller because there's only 2 things you got to measure that have error. Here there's 5 things you've got to measure that have error. The errors are simply adding the errors in the meter readings for resistance and voltage, as many as you have to for Kirchhoff's rules and Ohm's law. So that would be your error analysis.